Imagine if you could take a single molecule and trace it as it moves through the hidden machinery of modern civilization. Not oil, not electricity, but hydrogen. The smallest molecule in the universe, yet one that is now being positioned as the backbone of an entirely new industrial system. Now imagine following that molecule not inside a lab but across real infrastructure, through wind farms, electrolyzers, pipelines, liquefaction plants, ports, and chemical facilities, until it finally becomes fuel, fertilizer, or feedstock. This is not a theoretical journey, this is already happening. And three companies, Siemens Energy, Linde, and Shell, are quietly building the pathways that allow this molecule to move. This is where the real story of green hydrogen begins. Not at the electrolyzer, not at the solar farm, but across the entire chain that connects them. Because hydrogen is not valuable when it is produced. It is only valuable when it is delivered, stored, transformed, and used. And that journey is where most projects fail. Start at the beginning of the chain where renewable electricity is generated. Wind farms in Northern Europe, solar fields in the Middle East, and hybrid renewable clusters in Australia are producing massive amounts of electricity at increasingly low cost. This is the first critical condition. Without low-cost electricity, green hydrogen cannot compete. But even when that electricity is available, it does not automatically translate into hydrogen production. It must be converted. This is where Siemens Energy enters the picture. The company has positioned itself not just as an electrolyzer manufacturer, but as a systems integrator. Its role is not simply to split water into hydrogen and oxygen. It is to connect fluctuating renewable electricity to stable hydrogen production systems. That sounds simple, but it is not. Renewable energy is inherently variable. Wind speeds change, solar output drops at night. Electrolyzers, however, operate best under stable conditions. So the first hidden challenge in the molecule's journey is temporal mismatch. Electricity is intermittent, industrial demand is continuous. Siemens Energy's systems attempt to bridge this gap through power electronics, grid integration, and dynamic operation strategies that allow electrolyzers to ramp up and down without damaging efficiency or lifespan. This is not just an engineering problem, it is an economic one. Every hour an electrolyzer is not running reduces its utilization rate, and utilization rate is one of the most important drivers of hydrogen cost. Now imagine the molecule being created. Water enters the system. Electricity passes through the electrolyzer stack. Hydrogen is produced. At this moment, many narratives about green hydrogen would suggest the job is done. But in reality, this is where the complexity begins. The hydrogen produced is not immediately useful. It is a low-density gas. It must be compressed, stored, or transported. And each of these steps adds cost, energy loss, and infrastructure requirements. This is where Linde becomes critical. Linde is one of the world's largest industrial gas companies, and its expertise lies not in producing hydrogen, but in handling it. Compression, liquefaction, storage, and distribution are the domains where Linde operates. These are often overlooked in public discussions, but they are where a significant portion of project cost and technical risk resides. Take compression, for example. Hydrogen must often be compressed to pressures of 350 to 700 bar for storage or transport. This process consumes energy. It also requires specialized materials because hydrogen molecules are so small that they can permeate metals and cause embrittlement. This means pipelines, valves, and storage tanks must be designed specifically for hydrogen, not simply repurposed from natural gas infrastructure. Then consider liquefaction. To transport hydrogen over long distances, it is often converted into a liquid at extremely low temperatures, around -253 degrees Celsius. This process is energy-intensive, consuming up to 30% of the energy content of the hydrogen itself. Linde has developed advanced liquefaction technologies to reduce these losses, but the fundamental challenge remains. Every step in the chain reduces efficiency and increases cost. Now the molecule moves further along the chain. It leaves the production site. It enters storage or transport systems. It may travel by pipeline, truck, or ship. And eventually, it reaches its destination. This is where Shell comes into play. Shell's role in the hydrogen economy is not limited to production. It is building integrated systems that connect production, distribution, and end-use applications. In places like the Port of Rotterdam, Shell is developing hydrogen hubs where renewable electricity is converted into hydrogen, which is then used for refining, chemicals, and heavy industry. This is where the molecule finally becomes valuable, not as hydrogen itself, but as a substitute for fossil fuels in industrial processes. Hydrogen can replace natural gas and ammonia production, reducing emissions in fertilizer manufacturing. It can be used in refineries to produce cleaner fuels. It can power fuel cells in heavy transport applications where batteries are less practical. But even at this stage, the system is fragile. Demand must be synchronized with supply. Infrastructure must operate reliably. Contracts must be in place to ensure long-term offtake. This is where many projects face their greatest challenges. The hidden reality of the green hydrogen supply chain is that it is not a linear process. It is a network. Each component must function in coordination with the others. If one part fails, the entire system is affected. For example, if renewable electricity prices increase, hydrogen production costs rise. If electrolyzer utilization drops, capital costs are spread over fewer operating hours, increasing the cost per kilogram of hydrogen. If transport infrastructure is not available, hydrogen cannot reach end users. If offtake agreements are not secured, projects cannot achieve financial close. This is why companies like Siemens Energy, Linde, and Shell are not operating independently. They are forming partnerships, joint ventures, and integrated project structures, because no single company can manage the entire chain alone. Now consider the system under stress. What happens if subsidies are reduced? What happens if electricity prices spike? What happens if utilization rates fall below expected levels? These are not hypothetical scenarios. They are real risks that developers must consider. Under these conditions, only projects with strong competitive edges will survive. Utilization becomes critical. Projects that can operate at high capacity factors will have lower costs. Cost of capital becomes important. Companies with access to cheaper financing can sustain longer payback periods. Demand lock-in becomes essential. Long-term contracts with creditworthy off-takers provide revenue stability. System simplicity also matters. Complex systems with multiple dependencies are more vulnerable to failure. Projects that minimize integration challenges and rely on proven technologies may have an advantage. Time to deploy is another factor. Companies that can build and scale quickly may capture market share before competitors. This is the competitive edge test. If subsidies disappear, if costs rise, if utilization falls, which projects continue to operate? Which companies remain viable? The answer is not always the ones with the most advanced technology. It is often the ones with the most integrated systems. Now look at the future scenarios. If green hydrogen succeeds, it will not be because of a single breakthrough. It will be because entire systems are built and operated effectively. Ports will become hydrogen hubs. Industrial clusters will be connected by pipelines. Renewable energy will be directly linked to industrial demand. In this world, companies like Siemens Energy will provide the conversion systems. Linde will manage the molecules. Shell will connect the system to global markets. And the value will not lie in any single component, but in the integration of all of them. But there is another scenario. If these systems fail to achieve economic viability, green hydrogen may remain limited to niche applications. High costs, low utilization, and infrastructure constraints could prevent large-scale adoption. This is why the current phase of development is so critical. Projects being built today are not just demonstrations. They are prototypes for entire industrial systems. The lessons learned from these projects will determine whether green hydrogen becomes a foundational element of the energy transition or remains a specialized solution. Now return to the molecule. From the moment it is created to the moment it is used, it passes through a complex chain of technologies, infrastructure, and business models. Each step introduces challenges, each step requires expertise, and each step must be optimized to achieve economic viability. This is the hidden supply chain that most people never see. It is not visible like wind turbines or solar panels. It operates behind the scenes, connecting energy systems, industrial processes, and global markets. And this is why the companies building this chain matter. Siemens Energy, Linde, and Shell are not just participants in the hydrogen economy. They are architects of the systems that will determine its success or failure. If you are a developer, consultant, or investor trying to understand where the real opportunities and risks lie, you need to look beyond individual technologies. You need to understand the entire system. That is exactly what we break down inside H2 Hub by Renewable Energy, where we analyze real projects, cost structures, and system integration challenges to help you navigate the complexity of green hydrogen development. Because in this industry, success is not about having the best component. It is about building systems that work under real-world conditions. And if you want to go even deeper, the execution tools used by professionals, from project finance models to infrastructure planning frameworks, are linked in the description to help you move from theory to real project development.